For nearly 6 decades, in the remote Polish town of Frombork, Nicholas Copernicus meticulously filled notebooks with observations, calculations, and revisions. The result, a bombshell of a book titled On the Revolutions of the Celestial Spheres. This wasn't just another astronomy text, it was a quiet revolution waiting to explode. Copernicus knew his ideas were controversial. The prevailing view for centuries placed Earth, not the Sun, at the center of the universe. He proposed a heliocentric model where he placed the Sun in the center and the planets, including Earth, orbiting in a circular orbit. He understood the potential backlash his ideas could spark. Since challenging the long-held geocentric model supported by the Church was no small feat, he remained hesitant to publish his work during his lifetime. It was not until the year of his death, 1543, that his book was finally published. Placing Earth at the center of the universe resonated with the idea of humanity's special place in God's creation. It supported the belief that Earth was not just the center, but also the most important part of the cosmos, where God's greatest creation, humanity, resided. For almost 1,500 years, from ancient Greece to the Middle Ages, the idea of the Earth at the center of the universe dominated Western cosmology and astronomy. In medieval Europe, people's understanding of the world was shaped largely by the teachings of Aristotle, and the idea that the Earth was the center of the universe, based on the work of Ptolemy. From our everyday experience, the geocentric model, which places the Earth at the center of the universe with the Sun, Moon, planets, and stars all revolving around it, made sense. For one reason, when we observe the sky from the Earth's surface, the ground feels solid and stationary, and the sky appears to move around us. In everyday experiences, we do not feel Earth's rotation on its axis or its orbital motion around the Sun. The Sun rises in the east, moves across the sky during the day, and sets in the west, giving the impression that Earth is stationary. In the 4th century BCE, the ancient Greek philosopher Plato built upon the idea of a spherical Earth, already established in the astronomical world. According to Plato, the Earth was a sphere and a stationary object at the center of the universe. Around 200 years earlier, Pythagoras had also proposed spherical Earth, which he claimed based on his observation of eclipses. He also speculated Earth moved in a circular motion around an unseen fire. Pythagoras claims that the Earth moving in a circular motion was lost in time or not widely adopted in later eras. Building on these ideas, Plato took things a step further. He believed each celestial body, including the moon, sun, planets, and stars, resided on its transparent sphere. These spheres were believed to rotate at constant speeds along circular paths. One of the students of Plato, Eudoxus, introduced the idea of the transparent sphere. Eudoxus didn't use just one sphere per planet. He proposed a series of nested spheres, typically 3 or 4, for each planet, sun, and moon. By adjusting the speeds and directions of these spheres, they could mimic the observed variations in planetary movements. His homocentric sphere model influenced later astronomers, including Aristotle and Claudius Ptolemy. These spheres were imagined to be perfectly spherical and made of a transparent material, what he called ether, that filled the heavenly realm beyond the Earth's atmosphere. This substance was believed to be different from the earthly elements like earth, water, air, and fire, and therefore possessed divine properties through which the celestial bodies moved. Similarly, in later years, Plato's student, Aristotle, another famous Greek thinker, improved the idea of Earth being at the center of the universe. The geocentric model seemed to fit the world around us. Based on common sense, the Earth feels stationary, and the stars appear fixed in the sky. Nevertheless, this model struggled to explain why the stars wouldn't seem to move significantly if Earth itself were orbiting the Sun. Ancient astronomers did not detect significant shifts in the positions of stars relative to one another throughout the year. Two explanations could account for this observation. Either Earth remained stationary, or the stars were located at a much greater distance than previously believed. The ancient Greeks clearly underestimated the vast distances to stars. The immense distances meant that the apparent shifts were small, even when Earth moved across its orbit around the Sun. To understand this concept, known as the stellar parallax. Imagine you're driving down the highway and a car in the next lane zooms by. Its speed and direction are obvious because it's close. But trees, buildings, mountains, even though you're moving, they seem almost stationary. That's because they're much farther away. In space, it's similar. Nearby stars, like that fast car, show clear movement. But distant stars, like those faraway buildings, appear fixed in the sky.
Yeah, totally. That makes sense.
With advancements in telescopes and astronomical measurements, modern astronomers observe stars from Earth at different times of the year, about 6 months apart. They can see a slight apparent shift in the positions of nearby stars. These older models of the universe relied on a flawed concept, the perfect concentric sphere. This meant that celestial bodies were imagined moving in perfect circles around a central point. This perfect sphere idea didn't match what astronomers saw in the night sky. For example, planets appeared dimmer or brighter depending on their distance from Earth. Some planets, such as Mars, Jupiter, and Saturn, appeared to change in brightness over time as they moved across the sky. This variation in brightness could not be adequately explained by the celestial body's perfect circular orbit around the Earth. The second and most important observation that had baffled astronomers throughout the centuries was the irregular motion of Mars and Jupiter in the night sky. Once every 28 months, Mars appears to move backward in the sky. And Jupiter once every 13 months, relative to the distant stars. This motion is known as retrograde motion. These variations in brightness and irregular motion of Mars and Jupiter couldn't be explained by the principle of uniform circular motion. While Earth's orbital motion and the varying speeds of planets cause the illusion of retrograde motion. The traditional view of planets moving in perfect circles around a stationary Earth struggles to explain this phenomenon. Around 500 years after Aristotle, Claudius Ptolemy, a Greco-Egyptian astronomer and mathematician, popularized and standardized the geocentric model. In his monumental work, the Almagest, Ptolemy gathered various aspects of astronomy from across multiple civilizations and historical periods. This included centuries of observational data, along with his own findings. He aimed to resolve issues with previous versions of the geocentric model. In his model of the universe, he refined the concept of the epicycle and deferent to justify retrograde motion and the uneven speed of planets in the night sky. In his model, a simple circular path around Earth couldn't explain the observed variations in planetary speeds. With just a circular orbit, the planets would appear to move at a constant speed. To justify this observation, he imagined a large rotating circle, called the deferent, centered on Earth. This deferent carried a smaller circle, the epicycle. The planet itself is located on a smaller epicycle, which rides along a larger circle called the deferent. Both the epicycle and the deferent rotate. The key point is that the epicycle didn't revolve around the exact center of the deferent. Rather, it revolved around equant. This allowed him to explain the observed variations in planetary speeds. At certain points on the epicycle, the planet's motion on the deferent would appear to slow down, stop, and even reverse when viewed from Earth. Though not entirely accurate, this system provided a reasonable explanation for retrograde motion. However, the concept of the equant wasn't physically realistic. There wasn't a physical point in the universe where the epicycle magically revolved at a constant speed. The deferent is like a big gear, and the epicycle is a smaller gear attached to it. The planet sits on a peg on the epicycle, so it gets carried around by both the big and small gears. This system became incredibly complex as astronomers added more epicycles and deferents for different planets. Despite this, his model of the universe would serve as the standard astronomical text in Europe for the next 1500 years. However, by the 16th century, scientific advancements led to the heliocentric model, which placed the Sun at the center. This shift fundamentally reshaped our understanding of the universe and humanity's place within it.